Yeah, why is it that when you punch a wall with a bare fist, it hurts, but when you punch it with a glove, it doesn't hurt? Okay, first of all, there's a force on your hand because there's a change in momentum. Okay, so when you punch the wall, your hand is moving with some momentum, and then it stops, so it's got zero momentum. So in the case of a bare fist, this happens in a very short time. Your hand stops very quickly. So we say there's a fast rate of change in momentum. This leads to a large force. Okay, while with the glove, on the other hand, you have the same momentum going in and then it stops eventually. So the change in momentum is the same. However, because the glove deforms, it changes shape, your hand doesn't stop straight away. It takes a bit more longer to stop. So the time it takes to stop increases. So the rate of change in momentum is slower. So that means the force is slower. So your hand doesn't feel as much pain. Ultimately, all of these safety devices that protect you can be explained using this equation. So here, force is equal to rate of change in momentum. Now, in both of these scenarios, the change in momentum is the same. However, with the glove, the time taken to stop is increased. It's taking longer. Now, that's, as you can see from the equation, the force is inversely proportional to time taken to stop. So that means the force decreases and you feel less of force. So here's another example with something that's protecting your safety device that uses the same equation. An athlete is falling, he lands on the safety mat. Explain how the safety mat reduces the risk of injury. Like I said, it ultimately comes down to this equation, force is the rate of change in momentum. The time taken for him to stop with the safety mat is going to be longer. Well, if you without the safety mat, he'll just stop very suddenly. So the change in momentum is the same, so he's going to fall at the same speed. So the force, inversely proportional to the time taken, is going to decrease. So let's explain this. So first thing the safety mat is going to do is when he lands on it, it's going to deform. It's going to change shape. By changing shape, it's going to increase the time it took for him to come to a stop. So the same change in momentum, but takes longer to do that. So we say the rate of change in momentum is smaller. Now that's the rate of change in momentum. That's literally saying force. So we kind of repeating ourselves here at the bottom by saying the force is smaller, but it's just worth doing in case that's worth a mark in the exams. The second example, you've got state three features of a car that are designed to reduce the risk of injury if the car crashes. The first obvious one is the airbag. The airbag inflates when your car crashes, but then when you collide with the airbag, it's going to deflate. And then you've got the seatbelt. The seatbelt actually stretches if the car collides, and so your body moves forward ever so slightly and then stops. And then you've got a crumple zone at the front of the car. The crumple zone is an area of the car which is designed to, like the name suggests, crumple and come together when the car crashes. Okay, so how do these all work? Like I said, they all use this equation like all other safety devices. They increase the time taken for the same change in momentum and therefore reducing the rate of change in momentum and the force. So to explain this, first of all, in technology, all these things change shape. The airbag gets compressed, the seatbelt stretch, the crumple zone crumples, and they all increase the time it takes for the same change in momentum and therefore reducing the rate of change in momentum and reducing the force on any passenger. Okay, third and final example. The diagram shows a tablet. A company is designing a case for the tablet. State a property the case must have to avoid damage if it is accidentally dropped. Okay, ultimately we're going to use this equation. What we don't want is the tablet to hit the ground and stop suddenly. We want to stop over a slightly longer period of time. We want the time at the bottom of the equation to increase for the same change in momentum. So let's assume it's going to hit the ground at the same speed with and without the case. And this will reduce the rate of change in momentum and we're decreasing the force on the object. So what we want the case to do is to deform slightly so that the tablet doesn't stop abruptly suddenly. So it takes a longer time to stop. And this would, for the same change in momentum, this will reduce the rate of change in momentum and that will reduce the force. Now we're talking about even a millisecond here. That would reduce the force um, on the tablet quite a bit.